Hello and welcome to this third video about Apex. In this video we will be talking about Apex script, but before I explain what that is, I want to recap what we went through in the first and the second video. So in the first video, which was called the Introduction to Apex, we learned that we can create a graph using a stash node or an edit Apex graph node, which is just a wrapper around the stash. And we can then pipe that into this node called Apex invoke graph that then runs this logic. And if this logic or graph has some inputs, which we can define in here, then it outputs the result. And the result is always geometry in SOPs. And therefore, we also learned that the Apex graph can be represented as geometry, so we can share the graph between SOP nodes. And this is the very manual way, and we were creating nodes one by hand. In the second video, we had a look at the most sort of high-level version of rigging in Houdini, and that's called the auto-rig component. This is the automated way. And here you just set some parameters on the HDA, and you also prep your input, which is a KineFX skeleton. And the result will be a character stream, and we define that as some packed geometries with specific namings and specific contents with an updated rig. So Apex script kind of lands in the middle. It's great for making custom setups, but it's also designed to work really well with the auto-rig component. And how you work together with the auto-rig component and Apex script is a little bit outside the scope for this video. But just to mention, in the auto-rig component, you can set the component parameter to use snippet, and then you can write Apex script directly. And you can also use this secondary input on the auto-rig component. And if you input what we're calling a component script, and to use that, you set the component parameter to use secondary input. All right, so with that mentioned, let's have a look at an overview of how Apex script works. So here for the first input of the Apex script node, you usually input an existing graph. So here I've just taken a stash node and I've copied the graph that we made at the end of the first video where we made the sort of procedural extrusion setup. And so in Apex script, we can write some code. So here we loop over the nodes, and for the nodes that are matching our conditions, we are setting the node color in the graph to red. And not super useful, but just a very easy example. So that's what happens in here. And the output geometry here is the updated graph. So now we have a graph that has some red nodes. So in comes a graph, we do some edits with code, and out comes an updated graph. Now the next part might be a little bit confusing, but I think it's worth mentioning what is actually going on an even more lower level. So just try to follow along, and if what I'm saying here is not 100% clear the first time around, don't worry, you can still definitely work with Apex script and make awesome tools with it. So let's give it a try. So here I have the same stash and the same original graph. And in Apex script, we are finding all the nodes that start with extrude, and I have this wildcard, the star. So anything after is fine. And then we loop over those nodes we found here. And for those nodes, we set the node color to red, just like in the previous one. And here, I have unlocked the Apex script HDA itself. So this is the content of the Apex script HDA. And I've deleted some of the nodes just to simplify it a bit. The nodes that I've deleted are some validation and checking and stuff, but these are the nodes that actually does the job. This is what we need to understand. So first off, we have a Python SOP. We have a SOP that creates a dictionary, and we have some inputs. Those inputs are the inputs of the HDA here. And we have two outputs. This is output 0, so this is the first output of the HDA. and this is output 1, so that is the second output. When we write our code in this HDA here, that code is then read by this Python SOP. So you see the name of this string parameter that we are writing the code in is called snippet. So if you look in the code here, let's zoom in here, you can see that it looks for a parameter on the parent called snippet, stores that as a variable called snippet. And here, if you have a header, it will put the header string, the snippet that you have written yourself, and the footer together, just plussing strings. If you don't have a header, then the snippet is the same as code, and code is used in this line right here where it says AST, which is a module that side effects wrote, and parse, and then code. So parse meaning it takes in the code that you did and it runs through it, and now it outputs something new, and the output is an Apex graph. So it compiles the graph and then writes it to geometry. That means that the result of this Python node here is a translation of this text into an Apex graph. So I've taken a screenshot of it here. I just selected the Python node, and this is the output. So here we are loading in the geometry, and we are finding the graph, and we are finding the nodes, and here we are setting the colors to red, and then we are writing it back to geometry. So that is exactly what we are doing here. And the load from geometry and write to geometry, that is before and after, is called a header and a footer. That's just a setting in the Apex script. I will show it later. So that is added automatically, so you don't have to write that every time. So the code I've written specifically is inside of here. That makes sense. This is the header, this is the footer. All right. So what we have just created here is called a component script. And as I mentioned earlier, a component script is something that either creates or edits an existing graph. And in this case, we are loading in the geometry and then converting the geometry to a graph. So here we're working with an existing graph. Then it does some changes to it, and then it stores it back as geometry. This is a very, very classical example of a component script. And that component script is now inputted to the Apex invoke graph, the one we used in the first video. So here is some logic where we are doing some stuff. And then what are we doing some stuff to? Yes, the original graph, which is this one, input 1, which is the first input. So that's the original graph we had here. So we're getting this graph. We have some instructions of how to edit it. And then the result here is the updated graph, which comes out of the Apex invoke graph. And that is the updated graph. So now we have the graph and some of the nodes are red. But the Apex script has two outputs. So the first one is the result or the updated graph. The second, it's just giving us the ability to also store the component script, which is what this Python node does. It's literally the translation of this text into a graph. This is a confusing concept, and you might need to rewatch this a few times for it to make sense. Certainly for me, it took a little while to sort of get it. And don't worry if this was a lot. It is confusing. The good thing is that once you get this concept, you can see here that if you look at the inside of the auto component, it's doing the exact same thing. So here I simplified the insides of it because there are a lot of nodes, but most of the nodes are not needed for this explanation. So we are left with these three really important nodes. One is the component script. So remember in the second video, we are using this component dropdown, And all that is doing is pointing to different files on disk that comes with the Houdini installation. And those files are BGeo files, which are obviously geometry, and those are a component script. So if you look at the FK transform one, it takes in the graph here, and it looks for guides, it adds some nodes, it finds some nodes, it promotes some parameter, updates some tags, and at the end, it writes it to geometry. There's a lot more than just this because it's extracting the character stream, finding the base.rig, and that is what this graph is. And outside of this is kind of packing it back into the character stream and then storing that to geometry. But just to try to keep it a little bit simplified, this is pretty much exactly what the Apex script node itself is doing. But instead of loading a preloaded component script, we are writing it directly in the node. And this dictionary with the settings are the settings here in the parameter window. It just looks at the parent node, which is this one, and grabs all the settings, and that is used in the component script. So we have the character stream coming in here. It finds the base.rig because it's part of what this is doing. Adds the FK setup and then overrides the base.rig, which is the graph. And so here we have a character stream with an updated rig graph. Okay, let's jump into Houdini and get started programming. So we are back in Houdini and I have prepared an example scene here that I will be working in. So this is for the current video. I also added the examples from the previous videos. So for this video, we have already covered this part in the intro. So I kept it here for reference. Then from this block and to the last one is what we will create for the rest of the video. And this is kind of a step-by-step. And I have marked the code that I have added in each step. So these lines showing that. So whatever is between these lines is added in the current block. So hopefully it should be a good resource to use to come back and take it step by step. Now we will work down here for the video. I just have a line here and a rig doctor, and now we have a skeleton. I just dropped down Apex script node. So just a quick overview over the parameters here. This is where we will write our code. The next important setting is the header. Be sure to add that. So now we actually have written some code. This is our component script because the header is inserting actually a header and a footer, like we mentioned in the intro. It is loading the geo input and is getting a graph from the geometry. But in this case, there is no graph here. So this one will just return an empty graph object, which is totally fine. We need that anyways. And then lastly, it's just writing the graph back to geometry. And that's it. So I would always use this. We also need to bind the input in the settings. So remember, inside of this one, there's the Apex invoke graph, and the good old bindings that we used in the first video are just exposed under the invocation tab here. So we need to go to binding 1, and this input is geometry. So in our case, this is geo. And lastly, we will have to bind the output. And this is also the output of the component script. So it's this node output and it's set to geo. And that is defined in this last line here, bind output geo. So because geo is the output port of write to geo and then this. So we need to write output :geo. And you should probably save this as default. And one more thing before we get started. If you click question mark here, you get the documentation for the Apex script node. So you have a reference for the Apex script syntax here, which is great. If you go all the way to the bottom, you also have a list of all the Apex functions that you can use. If you go back here again and go to the function mappings, you can get overview over the object-oriented style of writing that I'm using in this video. So everything I'm writing in the Apex script node is available here. Alright, so in this video we will recreate the setup from the second video where we took a skeleton, created FK transforms, used the setPoint transform to update the skeleton, and then we add a bone deform like this. So very standard. I will skip the IK setup for now. While we are not doing anything new, the new thing is using Apex script, which is really awesome. So first up, I want to get all of the transform values from the skeleton. So if you go here and to the geometry spreadsheet, we all have this local transform and we have a name. So we need to transfer this to individual nodes in Apex. And to do this, I want to get the geometry here that I'm inputting to the script node, loop through it, create a transform object for each of the points, and set the name and the local transform. So to loop over points in Apex, the syntax is as following. For pt, this is just a variable name, geo.points, and geo.points is an iterator in Apex script, so you need to use that in the for loop syntax. Oh, sorry, and I forgot an in here. Okay, enter indent, and then we need to get name equals geo.point attrib value, and then we need to give it a point ID, which is just pt. This returns the point number or the index, and then we need to specify the name of the attribute we want to store the value for, and the name of the attribute is called name actually. There is an important thing here I wanted to mention. Apex doesn't know what type of attribute we are looking for. So by default, if nothing is specified, it will put down a dict for a dictionary. But we are looking for a string, obviously. So if we define the type like this, string, now this graph node here in our component script will change to string. So that's how you specify it. There are quite a few nodes like this where you kind of don't have to hardcode the type in the function call. It's just one function call, but it's depending on the definition of the attribute. So now we need to get the rest local. Let's do the same with that. Define this as a matrix 4. And this is the same, geo.point attrib value pt, and the name of the attribute is called local transform. So let's just write that, local transform. Let's see if this works. So this should return matrix. The next thing we need to do is to actually create the transform node. So again, here we are looking at the component script. So let's plot down a null and actually look at the result here. I hit F, there's nothing. Middle mouse button, you see here 0. We need to actually add the transform object node and then store the result. Let's call this just TO to keep it short. Transform object node equals graph, and then .add or update node. There's also something just called add node, but in case your node already exists, it will just update the values. And I think it's kind of a bit more safe to use this function call. So we need to give it the name, which is just the same as the name of the point that we just got. You need to give it the callback, transform object. It's very important that you write this correctly. So I like to add the edit graph here. This is extremely helpful. Then you do transform object like that. So now you can see exactly how it's spelled. And let's add this here. I just added an Apex network view, and let's pin this edit graph so we can keep adding stuff here and have this as a reference when we create the code. And we want to set some parameters on this transform object. If you hit P here, you can see it's just set to the ident matrix by default. But we need to get the local matrices and set it here in the parameters. So remember, parameters in Apex is just a dictionary called params. So let's just add that directly in the argument here. So we are just creating a dictionary called params, and it needs a key that is rest local. The key is matching the param here of the Apex node, so rest local. And we need to give the key a value, and we just got the value on the line above, so it's rest local. Another thing I want to add outside the scope of the for loop is just graph.layout. It just sorts the graph for us when we have more nodes. Okay, so now we have one transform object node per point with the correct naming, and you can also see here we have set some variables for the rest local. Let's connect this to a pack folder. It's a bit early yet, but I would like to show this step by step. So our Apex graph goes in here. This is basically the rig logic, and then the KineFX skeleton, which is the output of the rig doctor, goes in here, and we can give it the usual name of base.scale. And we can see now if we can actually animate this. So let's add down a scene add character. So now put that into the character stream, and now we have a character in an Apex scene. Let's call this Apple. Yeah, it's a logical name. And now we can do a scene animate finally. And let's swap this Apex network view back to the scene view. We have this here and activate the view state, and voila, we have nothing. And this is expected, because we have not promoted the inputs of the transform object. So the view state of the scene animate, it looks to see if our transform object TRS is promoted to a params node, and if it is, it will create a controller for each of them. So this is sort of a hard-coded behavior of the scene animate. It goes a lot deeper than that, but that's a simplified explanation. So let's promote the ports. So while still being in this loop, so for each of the transform objects node, we need to promote. So that's very simple. So transform object underscore node TO node. We need to get the input port. Let's get the reference here for this one. So we need to grab the T input, R input, and the S input port. And since we have the same name on both sides of the nodes here, we need to specify that it's an input port with underscore in. So let's say T underscore in dot promote. And now we can just give it a name. And we don't want to hardcode the name, because the name needs to be unique for each transform object. So we can use this very common Python syntax to make a dynamic string. So if you start with F, and then we have the curly brackets, and you input a variable that we have defined in our script. So in this case, I just want to input the name. So this will be evaluated to the value of that variable, and then we can add a suffix. So in this case, I want to hardcode that to T. So let's see what happened now. We still have an error that got stuck, doesn't matter. So for each of these nodes, we have a unique name and with the suffix T. And now we have 6 ports here. So let's go to the scene animate. Let's say reset all, go back to the scene view, go here, and we still don't have anything, which is kind of strange. I am thinking this might be a bug. Let's double check this. This goes to T. The scale doesn't matter in this case. I can actually delete it for now, just to simplify. And I'm gonna stop the video and figure out what's going wrong here. And I'm back, and you probably saw the mistake before I did. This input is not an existing character stream that's coming in here. It's just an Apex graph, so it needs to go into the multi-input like we established in the first video. And this should be base and rig. So now the Apex animate knows what to do with it, and it uses it to build the controllers here in the view state. And it looks like we have only 2 controllers, but as you can see, we have all the points, just because it's just a local transform that's set, and there's no parenting involved here, so they get the same position. So yeah, so far so good. Let's promote the rest of the channels. Say we want rotation and scale as well. Let's just copy this line and fix the indenting like that, and let's take rotation like that, take scale like that, and check the scene animate, just reset it, enter it. And now if you just take one of the points, we can rotate it, hit G to get the channel editor. You can see here now we can set all of the channels and also scale. So now let's parent up the transform objects. So again, I want to sketch this out in an edit graph. So we have a bunch of transform objects and we need to parent them up like this. So we need a world X form and a local X form that goes into the parent in and the parent local in. We need to find the hierarchy of the nodes from the SOP skeleton / KinFX skeleton. And also we need to note that the first joint in the chain does not have a parent, so we need to make a condition for that. So we are not trying to connect this to a joint that doesn't exist. So in our loop, we first need to check if it has a parent. So let's call that parent underscore point, and that equals to geo.getParent. So this is a function you can use in Apex, and it needs an index for the point. We already have that because we are in a loop. That's the iterated value here. And now let's look in the component script and find the getParent. This will return an integer, and it's the only port, so in most cases I would say we don't need to specify the type here. Now we can make our if statement, so we're gonna check if it has a parent, and this function will return -1 if it does not find the parent. So we can say if parent point is not equal to -1, then we can do stuff. We want to connect it up, so we want to get the parent name equals geo.point attrib value, and it's the parent point we want to get the value from, and the name of the attribute is again just called name. And as we established earlier, we need to define the type here, string, so we get the correct Apex node. Right, so we can call it parent node equals graph.find node, and the find node just needs a string, and this is the parent name that we got on the previous line. So let's see, this will not really create anything, but it will find stuff, but in our output we haven't actually written any connections or anything, so it looks the same. And now time to connect it up, so we can say parent node .xform underscore out, that's this output port right here, dot connect, and we want it to connect to the node that we are on, which is the transform object node, to underscore node dot, we need to get the import, which is the parent in. Let's see in the result here, yeah, they are connected, and 0, 1, 2, 3, 4, 5. So now we just need to do the same with the local X form to the parent local. So we can take this line here, make a new line, and say parent node dot local X form underscore out to parent local underscore in. I think maybe you could leave out the underscore out and in here, but it doesn't hurt to leave it in. Let's see, now we have 2 connections, perfect, and that's it for the parenting. So let's look in the scene animate, see if this is any better. Go to the view state, and yeah, let me hide the settings here again, Control G. This looks like a hierarchy, but we can't see the original skeleton that we inputted, this one right here. It could be nice to see that deforming as well, so we're sure we're actually writing out the results. So right now we are just setting some view state handles here, but we're not writing out to SOPs again. So let's take care of that. And this node where we write the X forms back to the KinFX skeleton is called setPointTransforms. So let's add that here, setPointTransforms. And this is a very unique node because first of all, it has this square in front of geo, which means that we need to sort of stash the value coming in with a value node. So we need to add value geometry. So if we had, for example, a parms node, which I haven't added yet, parms. Yes, I always forget this. In the tab menu, it's called input and output, parms and output. The callback is parms. So let's say we have like a base.scale coming in here. So like we have established already, base dot whatever. if we input the skeleton, it would be base skell, like that. So now we can get a reference of that value, and we need to stash it, and then it goes into the set point transforms. The details of why this is necessary, it's a bit above my understanding of Apex graph at the moment. But as far as I know, if you don't have this, it will kind of override itself, and it needs a reference of the original value. I think it has to do with the execution order and some optimizing. But yeah, the second part that is unique with this node right here is that it has something called a variadic input port. And this is a type of input port that when you connect a new node to it, it will create a new port. And we can connect each port here, and we'll by default take the name of the variadic port group itself and then just add an index. But the node here itself, it is actually going over each of these ports, and if it finds a point that have a name attribute value which is the same as the value of the port. So in our case, in our rig, we called it point_0 and point_1. So in our case, now we would say, oh, I have a point in the geostream that is incoming which has the same name as the name of this port. Then I will update the point transform attribute. And this is quite confusing when you see it the first time. This is sort of a thing that you see quite a bit in Apex, and the whole point here is to flatten any hierarchy instead of doing this through a loop. It's like a flattened thing, so you can have a million inputs to this and it would still be fairly quick because it's not in a loop. Yeah, so that's what we're going to do with Apex script right now. So first of all, we need to add the set point transform and the value node and connect this up to base.scale. So let's do that first. And this should not be part of the loop. So let's do this before the loop. Let's call this spt_node equals graph.add node. And it needs a name. Let's just call it spt. And then it needs a callback. We can already see that here is scale : set point transforms. So let's write that, scale : set point transforms. All right, let's see if it actually added a node for us. And let's see here in the output, we have a node and it has ports and it looks like what we just had here. So that's good. And we need the value node. So I'm going to call it scale_freeze. Then I know it's a value node that is connected to this squared input. That's just my naming. Graph.add node, and the name could be scale_freeze, and then the callback, as you can see up here, is value geometry. Okay, let's check that in the result. And both these new nodes have ports and everything. It looks good. So let's connect it up. So we want to go from the output to the input when it's two normal nodes we are connecting together. But if we are connecting a node to the params or the input node or to an output node, we need to use a function called promote. Okay, so let's connect up these two nodes first. So we want to start with the value node, which is the scale_freeze dot. We need to get the output port. It's named value. It's a unique name, so we can just type value dot connect, and we need to connect this to the spt node. So spt node dot, and here we have two ports named the same, so we need to specify it's the input port, so it's geo_in. So let's see if this worked. Oh, there's a typo here. I misspelled this variable name, and I will leave all of my mistakes in the tutorial because this happens a lot when you're working with Apex script. Again, I think this just stuck. Middle mouse button click. It's okay. So now they are connected. Yay! Now let's just promote the input port here that is called param. So yeah, let's just copy the name of this variable and say param.promote and the name of the port we want to promote, which is going to be base.scale. So this is getting the value of the base.scale input, which is the Kinefx skeleton. And let's check the result. This looks good to me. So for the next part, we need to connect up all of the transform objects. So we need to take this output xform port and put it in here and name it. And this has a unique function in Apex. And this is something we do inside of the loop. But we don't want to do it inside of this if statement, because even though this node, the first joint here doesn't have a parent, we still need to connect it up. So let's just make a new line outside the scope of the if statement. And there is only one function we need to add here, and that is graph.find or connect input. So this is the function you need for variadic inputs, and it has a bunch of arguments. So let's add them here. Actually, let's remove those lines again, and I'm going to start here. So I'm going to call the first one src node equals, and this is something I got from the documentation. I would never remember this, but the source node is the transform object node that we have defined. And the second argument is called source name, src name, and that is just xform, because that is the output of the transform object node. So that's the one we want to connect from. All right. Then destination node, which is the set transform node. So like that equals, and we already have a variable for that, spt underscore node. And we need a destination name. And this is, think of this as sort of the apparent group for all of the variadic ports. So in case we had different variadic port inputs on the same node, we need to define which one it is. In this case, it's just one, but it's called transforms. That argument is destination name, dst name, equals string transforms, like that, comma. And the last argument is the name of the new port we are creating. It's not called port name in this case, it's called destination alias, dst alias. In this case, we already have the name because it's the name of the joint, which is the name of the transform object node. And we already have a variable for that, just called name. And we can close it off. So if we look at this and we have an error, the given function find or connect input does not exist because it's called find and connect, not or. So let's try again. Graph transform object node has not been defined because I called it TO node. So let's TO underscore node. And now it works, but it's still stuck on this error. You can see here we have the set point transforms node, and it has all the inputs, and the name of the port is the same as the name of the transform object, which is the name of the joint. So that leads us to the next step, which is to add the bone deform. But just to prove that it works, let's go to the scene animate. Maybe just reset it, go to the view state, and we cannot see the skeleton yet. So let's see here, we have the base.skeleton. We haven't outputted the updated skeleton. So we can do that. Let's do that at the end maybe. So we can do spt underscore node dot geo underscore out dot promote, and the name of the port is base.skeleton, for example, because the scene animate viewer state knows what to do with that, so it should show it. Let's try to output that. Oh, I also did a typo here. Dot. Yeah, I know you see it. It's worth mentioning in the scene animate, if you only have base.skeleton output, it will show it, but if I also had a base.shape, it would hide the base.skeleton and show the base.shape. That is also something that is hard-coded. Now, let's add the bone deform, and let's go back to the script node here, and let's add the node before the loop. Let's just call it bdef underscore node is graph, add node. Let's just call it bone deform, and the callback, which I never remember. Let's go here to edit graph and add a bone deform. Callback is SOP : bone deform, all lowercase. So SOP : bone deform. So let's see if it added a new node for us, and it's here and it has all the ports, so that is working. We covered before that this bone deform Apex graph node is of the type a SOP verb, so it's meshing exactly with the SOP node. So these three inputs here are the same as in SOPs. So let's make a SOP node, bone deform, and here we have some tips for what the ports are. Geometry to deform is the first one. So that is the incoming base.shape. The second one, if you look at the bottom, is a rest point transforms, means the rest skeleton. And the last one is deform point transforms, basically the post or the animated skeleton. We need to connect the first one to a port called base.shape. And the second one is the rest skeleton, so that's just this one. And you see here the icon for the ports are round, so we do not need to use this freeze geometry here. The last one is the animated skeleton, which is the output of the set point transforms. There you go. And lastly, we need an output node, and this now should be base.shape, like that. So let's do this with the Apex script, should be fairly quick. Let's connect it at the end here, and after everything has been connected up, let's take the first input of the bone deforms and promote it to base.shape input. So bdef.geo input 0, which is the name of this port. And I can say promote. And the name of the port is base.shape, like that. I got an error. Okay, doesn't like the port name. So let's try to add underscore in. Did that work? Still an error. Oh, the name here is wrong. It's underscore node, bdef underscore node. My mistake, node here. I think it might error out if we remove the in. No, that actually worked fine. This is not connected to the input here. And the next one is the rest skeleton. So we can take this one, copy it, and so the second one goes into base.scale, like that. Okay, it goes to base.scale, great. And then the last one, we need to get the output of the set point transform. So, and connect to the last input of the bone deform. So spt underscore node dot geo. So here, yeah, the output is geo underscore out. This time we need to specify it's an output, and we need to say connect. This is a function, and the argument is the input port. So that is bdef.geo input 2, which is the last input port. So let's see, we got an error. I forgot to add underscore node, like that. And now it works. All right, we have this. So the only thing we need to do is to output the result, which is from geo. Let's add this here. We can just actually copy this line because this is fairly similar. Bone deform node base.shape instead of skeleton. And now this works. Yay. And this error should disappear. Let's reset the cache here. Scene view. But there is nothing to bone deform, obviously, so let's steal the sweep node I showed earlier. So let's just take these two right here. So we need some geometry for the bone deform to work on. So let's sweep the skeleton, and it creates some procedural geometry. And we also need to add some capture weights to it. So the quickest one is just the joint proximity, joint capture proximity, like that. We have the geometry, rest geometry, and the rest skeleton here, and that is inputted as base.shape. So we need this base shape. So now this input port in our Apex graph called base.shape actually has some data on it. So now we are inputting this skin geometry here. Okay, so now let's go to the scene animate, recache it, and this should now deform. So far, so good. In my example here, I'm ending with this node right here, which is pretty much exactly the same as what I just made. I have also this setup where I added a pack folder and the scene animate, just like we did down here. And I just added these nulls to give it a bit more overview. I'm using the joint capture by harmonic, which usually gives a better capture, it's just a bit slower. And for the last example I want to show you, and we are getting to the end of the video, I know it's been a long one. I set up the switch that has different inputs, just a line with a noise, for example, and a spiral, and an L system SOP. And our little FK autorigger here can now take any input which has the recipe for being a joint. So it needs a name here and a transform. And here I'm using the same setup as from the second video, where I'm excluding the last points in the chains. So I don't get a controller on that one. I don't need it. Here I'm just skinning it. And here is the FK setup. And in this setup, I added a bone deform with a different node, just to show a bit more complex example. So imagine you have a node for lots of different stuff, and you kind of procedurally want to add deformers, but you want the deformers to be sort of in the order of your Apex nodes, very much like in SOPs. So this one procedurally just adds a bone deform at the end. So it does that by looking at the output ports. It's looking to see, looking for the name here in the ports, and if it finds it, it just gets this connection here and it fuses in the bone deform. So no matter what's in front, it will dynamically add it here at the end. So yeah, have a look at this if you're interested in going further with this. And then is the usual nodes. We have the scene animate, like I showed in the beginning of the video. So let's reset that and go back to the L system. And it takes a second with the biharmonic capture, is the one that is actually slow here. And now if you go into this one, we have another rig, which is very nice. And just to round it off, if you want to get this out to subsland, you can see here when you're not in the viewer state, so viewer state deformed, click escape to get out of viewer state, it's back to the packed one. What you're seeing here is actually just the packed folder. And to get the deformation, you can put down a scene invoke, this time instead of Apex invoke graph. This is a bit simpler, but it expects the input to be organized as an Apex scene, which we talked about has this kind of hierarchy here. And it will output you an invoked version of the base shape if that's what you specify here. You could also just click output all character shapes. I will grab it for you. And then you need to unpack that twice, so use the unpack folder, and now you have your geometry as points. And now you can work with it like you do with your normal subs nodes. Yeah, so that was a lot to cover. I would highly recommend you again to take a look at the documentation, and hopefully this step-by-step explanation of what I did down here proves helpful. So hopefully there are a lot of more videos to come, and I can't wait to go even more advanced into Apex script and the whole Apex world, because we are still just seeing the very, very little tip of the iceberg. There are so many tools. So I'm super excited about this, and I hope you are too. And yeah, hope to see you in the next one. Cheers and goodbye.
The only reason we can afford having Magnus spend a ton of time creating this course for you is the amazing support that we get from our patrons. So if you want to ensure that we can do stuff like this in the future and also get access to a ton of other courses about KineFX or Vex or Houdini in general, please consider joining our Patreon. And a very big thank you goes out to all our existing patrons. Without you, Entagma would not be possible. Thank you.